Ghost Law Explained. Have you ever looked up at the night sky or down at your own hand and wondered why any of this holds together? Why isn't the universe just a chaotic, fizzing soup of random energy? The stability we take for granted, the fact that atoms form, stars burn for billions of years, and the laws of physics are the same today as they were yesterday, is one of the deepest mysteries in science. The answer, according to theoretical physics, isn't a force we can see or a particle we can detect. It's an invisible, all-pervading principle of absolute perfection. A silent, cosmic guardian we can call the universe's ghost law. Now, this isn't about spirits or the supernatural. The ghost law is a powerful metaphor for one of the most profound concepts in modern science, a set of fundamental, perfect symmetries woven into the very fabric of reality. These aren't just elegant mathematical ideas scribbled on a blackboard. They are the unyielding constraints that prevent our universe from tearing itself apart at the seams. To understand this, we first need to redefine what symmetry means to a physicist. We're used to thinking about symmetry in a visual sense, like the perfect reflection in a mirror or the six-fold pattern of a snowflake. But in physics, symmetry goes much deeper. A physical system has a symmetry if you can change something about it, yet its essential characteristics and the laws governing it remain identical. Imagine you're in a windowless room conducting a physics experiment. If someone secretly rotates the entire room, your experiment will still yield the exact same results. This is rotational symmetry. If they move the room to a different city, your experiment still works the same. That's translational symmetry. These might seem obvious, but they are the first clues to a much deeper truth. The laws of physics don't care where you are or which way you're facing. This invariance, this refusal to change, is the heart of a physical symmetry. The ghost law emerges from the most fundamental theory of matter and forces we have, quantum field theory, or QFT. In QFT, the universe isn't made of tiny billiard balls called particles. Instead, the universe is filled with invisible, energetic fields. There's an electron field, a photon field, a quark field, one for every fundamental particle. What we perceive as a particle, like an electron, is just a localized, vibrating excitation of its underlying field, like a ripple on the surface of a pond. The rules that govern how these fields vibrate and interact with each other are the fundamental laws of nature. And this is where the ghost law truly reveals its power. The most important rules in QFT are not written as "thou shalt do this," but as "thou shalt remain the same even when this changes." They are written as symmetries. The deepest and most powerful of these are called gauge symmetries. This is a notoriously tricky concept, but we can use an analogy. Imagine mapping the height of a mountain range. You can measure every peak's altitude relative to sea level. Or you could measure it relative to the highest peak, Mount Everest, or even relative to the center of the Earth. You can change your 0 point, your gauge, however you like. But no matter which one you choose, the physical reality of the mountain range, like the actual height difference between two peaks, never changes. This is a gauge symmetry. In physics, fields have similar properties. You can make specific, abstract mathematical changes to them at every single point in spacetime, but the resulting physics, the forces, the interactions, the reality we observe, remains perfectly, absolutely unchanged. This might sound like an abstract mathematical game, but it has staggering consequences. A brilliant mathematician named Emmy Noether proved that for every continuous symmetry in the laws of physics, there is a corresponding conservation law. It's a cosmic contract of the highest order. The fact that physics is the same if you move through space directly leads to the conservation of momentum. The fact that physics is the same if you move through time gives us the conservation of energy, the unbreakable rule that energy cannot be created or destroyed. The strange, abstract gauge symmetry of the electron field and the photon field is what gives us the conservation of electric charge. These aren't just disconnected rules, they are the direct, physical manifestations of the universe's hidden symmetries. They are the tangible evidence of the ghost law at work. So, what would happen in a universe without this law? What if these symmetries were not perfect? It would be a catastrophe of unimaginable proportions. Without temporal symmetry, energy could pop into existence from nothing, leading to runaway chain reactions that would vaporize the cosmos in an instant. Without the perfect gauge symmetries of the Standard Model, particles might not have consistent charge, or forces might change strength randomly from one moment to the next. The very concept of a stable atom would be impossible. Reality would lose its coherence, its structure, its very meaning. It would devolve into a lawless, unpredictable chaos. The ghost law, this principle of perfect, unwavering symmetry, is the invisible framework that holds back this oblivion. It is the silent, perfect architect of our stable, structured, and comprehensible reality, setting the stage for the intricate dance of matter and energy that allows for our very existence. Symmetry preventing collapse. Having established that this ghost law is the universe's commitment to perfect symmetry, we can now ask the crucial question: how does it actually? How does an abstract mathematical principle physically prevent reality from collapsing into a chaotic mess? The answer lies in how these symmetries act as the ultimate cosmic rule makers, imposing strict, non-negotiable constraints on the behavior of everything from the smallest quantum jitters to the largest galactic structures. They are not passive observers, they are active guardians, policing the universe and preventing interactions that would otherwise be catastrophic. Let's start at the deepest, most fundamental level, the quantum realm. Here, reality is a frenetic dance of uncertainty, a place where particles constantly pop in and out of existence in the quantum foam. These are virtual particles, fleeting fluctuations in the quantum fields. In a universe without the ghost law's strict symmetries, this quantum foam would be an engine of pure chaos. A virtual particle could pop into existence and decide not to disappear. It could spontaneously gain enormous energy from nothing, violating the conservation of energy and triggering a runaway cascade. An electron could randomly decay into a shower of other particles that don't add up, violating the conservation of charge. The very vacuum of space would be unstable, constantly boiling with real energy and matter, making the formation of anything stable, like a proton or an atom, utterly impossible. But the ghost law forbids this. The symmetries we discussed, the gauge symmetries of the Standard Model, act like cosmic traffic cops. They dictate exactly which interactions are allowed and which are forbidden. They ensure that when particles interact or decay, fundamental quantities like charge, momentum, and energy are perfectly conserved. An electron can't just vanish because that would violate the symmetry that guarantees charge conservation. These symmetries force the quantum world to be orderly and predictable, taming the wild uncertainty of quantum mechanics and providing the stable subatomic foundation upon which our entire reality is built. We can think of it like a perfectly spinning top. Its rotational symmetry is what gives it stability. As long as it is perfectly balanced and the symmetry is unbroken, it spins smoothly and elegantly. But if you introduce a tiny imperfection, a slight asymmetry in its mass distribution, it begins to wobble. The wobble grows, and soon the top clatters and collapses. The universe is like that spinning top, but on an infinitely more profound scale. Its stability is a direct consequence of its perfect inherent symmetries. The ghost law is the principle of that perfect balance. It prevents the catastrophic wobbles, the forbidden particle interactions, the violations of conservation laws that would cause the entire system to collapse. It is the silent, constant enforcement of cosmic equilibrium. Now, let's scale up from the quantum world to the cosmos at large. The ghost law's influence is just as critical here. The force that governs the universe on the grandest scale is gravity, described by Einstein's theory of general relativity. And just like quantum field theory, general relativity is built upon a foundation of profound symmetries. One of its core principles is that the laws of physics are the same for all observers, regardless of their state of motion. This symmetry ensures that the fabric of spacetime is a smooth, continuous, and predictable canvas. If this symmetry were broken, the consequences would be terrifying. Gravity might pull stronger in one direction than another. The structure of spacetime could become fractured or lumpy, with regions where gravity simply ceases to exist and others where it becomes infinitely strong. Galaxies, which are held together by a delicate balance between the gravitational pull of their matter and the momentum of their stars, would be torn apart. Stars and planets might not even be able to form in the first place, as the gravitational collapse of gas clouds would become an unpredictable, chaotic process. The very expansion of the universe could become erratic, with some regions flying apart while others crunch back in on themselves. The stable, majestic cosmos we observe would be replaced by a disjointed, violent spacetime nightmare. The symmetries at the heart of general relativity, another facet of the ghost law, prevent this. They ensure that gravity behaves consistently across trillions of light years, providing the stable arena necessary for cosmic structures to form and evolve over billions of years. Ultimately, the ghost law is the reason our universe is fine-tuned for existence. The precise values of the fundamental constants, the speed of light, the strength of the electromagnetic force, the mass of the electron, are not random. They are believed to be the consequences of the universe's underlying symmetrical structure. A slight break in one of these symmetries would be like changing a single digit in the universe's source code, causing the entire program to crash. A universe with a slightly different symmetry might be one where atomic nuclei instantly fly apart, or where stars are impossible. The fact that we exist to ponder these questions is perhaps the most powerful evidence for this hidden order. It is an unseen, unfelt, yet absolutely essential architecture. This perfect, ghostly symmetry is the silent protector of reality, the invisible law that holds back the void and allows a universe of structure, complexity, and life to flourish.